Welcome back, everyone. So I had a request to cover rotation calibration, and so that's what I'm going to discuss in this video, specifically what it is, why it's important, and of course how to do it. So I want to start by showing you this slide that I took from a course I teach, and what you're seeing on the left is a bright field TEM image, a conventional image, and it's a sapphire wafer with a coating of amorphous carbon, and then on top of that a layer of platinum that was deposited using a focused ion beam. And then on the right you see a selected area diffraction pattern that was taken from the sapphire. And so you'll also see in each of these images, you'll see a pair of arrows. One is red and one is blue. And that's of course to denote that they are different directions. So what we're interested in often when we're doing TEM and when we're doing diffraction is we're interested in the relationship between the diffraction pattern and the image. So without going into a lot of detail, when you're looking at the diffraction pattern from a sample, you are in effect looking at its reciprocal lattice or reciprocal space. And so your actual sample, of course, has a real lattice, and so we want to then know how the direction in the diffraction pattern corresponds to a direction in the actual image. So if we look at the image and the diffraction pattern, what we see is that the red arrow in the image is parallel to the red arrow in the diffraction pattern, and the same thing for the blue arrow in the image and the blue arrow in the diffraction pattern. So what this in effect means is that if I know the direction in reciprocal space that corresponds to the red arrow, I know how that direction occurs in the actual image, and the same thing with the blue arrow. So one thing also to note is that I have the direct beam blocked off using a beam stop. I did try to put the start of the arrows over where the direct beam would be, but I have the direct beam blocked off, just FYI. So in this particular image diffraction pattern combination, it's set up such that the orientation between the image and the diffraction pattern is already established and does not need to be corrected. Okay? So one of the properties of our lenses in our TEMs is that they rotate images when they change strength. And so what that in effect means is that if I'm acquiring an image and then I acquire a diffraction pattern, I might not actually have the orientation between how I'm observing the diffraction pattern and how I'm observing the TEM image be what they actually are. And so when we calibrate this, there's a rotation between the image and the pattern that I have to adjust so that I can establish the correct parallelism between the image and the pattern. And so that rotation is what's known as rotation calibration. Now the good news is that if you have a brand new microscope that's manufactured today, doing rotation calibration is completely unnecessary because the engineering of the microscopes is such that this is accommodated into the technology. So in other words, whenever you get an image and you get a diffraction pattern, you don't have to rotate one relative to the other to establish the parallelism. But if you have an older microscope, and specifically if you're watching this, you probably have a Tecnai, then this is something that you will need to do. If you have I did work on a Joel 2010F. On the Joel 2010F, it's not necessary to do this. The Joel 2010Fs do not need rotation calibration, but the Tecnai instruments do. I did also work on a Joel 200CX for a number of years, and that's a very old instrument, and that also needs rotation calibration performed. So the amount of rotation that you're going to need to establish the parallelism in general will depend on the indicated magnification of your image and the indicated camera length of your diffraction pattern. So in other words, for any given combination of indicated magnification and indicated camera length, I'm going to have a necessary rotation angle between them. And how you define the rotation is purely arbitrary. You could rotate the image relative to the pattern, or you could rotate the pattern relative to the image. What I'm going to show you today, I rotate the pattern relative to the image and keep the image fixed. The good news, if you're working on a Tecnai though, is that when you start in M mode and you go all the way through MH mode, the image never rotates. Okay, so the orientation of your image never changes irrespective of your indicated magnification. Again, as long as you're in M mode through MH mode, and of course SA mode is included in there. And those are basically the bulk of the magnifications that you're using for imaging anyway. The other good thing about the Tecnai is that the rotation of your diffraction pattern basically has two different regimes. So basically there's a cutoff camera length where above it I have a constant orientation that doesn't change, but if I go below it, there is a rotation to the pattern. But if I go lower than that, I don't see any change in the orientation. So what that in effect means is if you're doing this on your Tecnai, there's essentially two calibrations that you need to do, okay? Because my image rotation never changes as a function of magnification, but my diffraction pattern rotation does change as a function of indicated camera length. Again, it's stepwise. So basically, there's a regime where it's one orientation, and there's a regime where it's another orientation. So then we have to perform two calibrations. I should also note that this may depend on the configuration of your Tecnai. On the one I'm going to do this on, this was done with a 200 keV instrument with a super twin lens. This is likely dependent on your objective lens configuration as well as the voltage you are operating at. So now that we've discussed what rotation calibration is, what do we need to do to perform it? Well, you need a single crystal specimen. You can't do this with a polycrystalline specimen. It has to be single crystal. And you have to have an understanding ahead of time of how a direction in the image of the specimen corresponds to a direction in the diffraction pattern. So if you have that information, and again, it's a single crystal specimen, you can perform the rotation calibration. So our test specimen is going to be a wafer of single crystal silicon, and on the right here in digital micrograph you see it's not technically a bright field image, it was taken with a multi-beam condition, so technically that would be a high resolution image, but you see an image of the specimen, and so that dark strip is actually a film of gold, which we're not interested in because it's polycrystalline, but to the left of the gold is actually the single crystal of silicon. And so I know, based on the orientation of the wafer and how I align the sample in diffraction mode, what zone axis I'm looking down and what my diffraction pattern is going to look like so I can establish the correct parallelism. Now on the left, I have the selected area diffraction pattern that I recorded from the silicon, and it corresponds to roughly that area indicated by the circle in the image. So this is my test specimen. This is the diffraction pattern that I got from that test specimen. And now I know ahead of time what the diffraction pattern should look like and how it correlates to a direction in the actual image. Okay, we're going to go ahead and start the video. So again, that's where my selected area aperture was, and that's the selected area diffraction pattern. So now what I'm going to do is take my line tool here, and I'm going to draw a line. So that direction right there, that nice straight direction, I know how that should correspond in the diffraction pattern, and I know it happens to be oriented how I'm drawing it like this. So what we can see here is that the line I drew in the image is not parallel to the line I drew in the diffraction pattern. So I have to rotate one relative to the other. Okay, so I'm going to again rotate the pattern relative to the image. So now by doing a little math here, which isn't very difficult, what I end up finding out is that I have to perform a counterclockwise rotation of my diffraction pattern of 90 degrees. So if I click on my diffraction pattern, I can actually do a digital rotation. I go to Process, and then Rotate, and then I put in 90 degrees counterclockwise. Click OK. And now I'm going to do a quick digital adjustment of my diffraction pattern so that it's a little more aesthetically pleasing. Just change my contrast limits. And now I can take that line from the image and copy it over onto the pattern. And now we see that I now have the parallelism that I expect. Okay, so we've correctly deduced one calibration. Now again, I know that there is a cutoff camera length where my pattern rotation is different, so I have to do this again for my other camera length regime. Okay, so you can notice the pattern on the right is taken with a smaller camera length. So now again, I have to figure out where the direction is in the diffraction pattern that corresponds to the direction in the actual image. And it happens to be right there. And we can see, of course, that my two lines are not parallel. So I can do, again, a little bit of math here, which isn't that difficult. And what I find is, again, I have to do a counterclockwise rotation of my diffraction pattern, but this time it's actually about 30 degrees. So I come back to the diffraction pattern and I do the same thing I did for the higher camera length. Again, process, rotate, and now counterclockwise of 30 degrees. I can again do a digital adjustment to make my pattern look a little bit nicer. And now if I copy that line over from the image, it fits exactly how I want. So again, I've now established the correct orientation between the image and the pattern. Now, one thing I do want to point out is that we saw how if we rotate the pattern 30 degrees counterclockwise, we can get the two lines to be parallel. But I could just as easily have rotated the pattern 150 degrees clockwise and gotten the exact same result. So which of those rotations is the correct one? Well, if you're talking about a selected area diffraction pattern, then it really doesn't matter too much which one you pick. But if you're talking about, for example, a convergent beam electron diffraction pattern, then it becomes extremely important to make sure that you've properly selected the rotation angle. So one of the things we saw in the demo on CBED was how we can reveal additional symmetry information of our material that we can't get with a selected area diffraction pattern. So if we're working, for example, with a crystal that doesn't have inversion symmetry or it has polarity, and we're collecting a CBED pattern from it, and we want to properly know the polarity with respect to the image, then we can't just pick one of those two rotation angles and have it be correct. Only one of them is actually correct. So then the question is it a 30-degree counterclockwise rotation or a 150-degree clockwise rotation? So how do we actually figure out which one it is? And so the way we do it is we use a little trick. So it's a little difficult to actually show this in the video, so I'm going to describe it first. So right now, I'm basically perfectly aligned with the zone axis. So what I'm going to do is I'm going to deliberately adjust my alpha tilt so that I'm not aligned with the zone axis. Again, I'm picking alpha because my sample is in principle eucentric with an alpha tilt adjustment. So what happens when I do that is I end up creating a ring or a circle in my diffraction pattern, which is called a Lowy circle. Okay. So the trick is, though, I can actually see the Lowy circle in my image when I bring the beam to crossover. So again, what I'm doing is I'm tilting off the zone axis with my alpha tilt. Doesn't have to be a lot, maybe a degree or two. And then I'm bringing the beam to crossover on my sample. And so I actually can see in the image, without going into diffraction mode, I can actually see the Lowy circle that I can see in the diffraction pattern. And that will allow me to establish and know once and for all which rotation angle is actually correct. So if you're going to do this, you have to be really careful. Okay, so I'm adjusting my spot size. I'm up at 9, really low current. Again, I'm bringing my beam to cross over on the sample. You can't really see it, but I also have my beam stop in. And so my beam at crossover is now under the stop. So when I acquire this now with the camera, I'm not at risk of burning the camera. Okay, so again, I'm in imaging mode. I'm not in diffraction mode. Okay, you can see I'm in SA mode here. And I have my beam stop in. I'm going to lift up the viewing screen here. Okay, and you can see now, you can see I have a ring or part of a ring. See how that ring is curving that way to the left? Okay, so that's actually the Lowy circle I see in the diffraction pattern, and then when I do an acquire, I see this. So that's really obvious right there, that ring. So on the right, that is what I recorded in image mode. Okay, again, my beam at crossover, you can see I have the beam stop that's blocking out the beam, and I can see the Lowy circle curving to the left. But then on the left, that is actually the diffraction pattern taken in diffraction mode with a parallel beam. So that's my selected area diffraction pattern. And we can see now that ring of spots, okay, that ring of the Lowy circle, except now it's curving upward. So by doing this, I insert an intentional asymmetry into the diffraction pattern. So now there's only one unique rotation that I can use in order to get the parallelism between the pattern and the image. Okay, so now I have the ability to correctly deduce which way I'm supposed to rotate my pattern. So I'm not able to pick between two possibilities. It's only now one possibility. So we'll start the video again. We see that's curving to the left. Make a little adjustment here to make it easier to see. That's curving up. So again, if we're rotating the pattern relative to the image, we can see now that that has to be rotated counterclockwise 90 degrees. Or conversely, 127 clockwise, that would be valid. Those are the same, they're not unique. Okay, but now we have correctly figured out the rotation calibration. Now again, this is one of the calibrations. So now I have to do the same thing, but I have to do it for the shorter camera lengths. So again, I can see now the Lowy circle there, okay, curving up and to the left. So we can see now that again, if I do a rotation of the pattern 30 degrees counterclockwise, I end up with the pattern oriented correctly. So it turns out that our initial guesses between our two possible angles were indeed correct. And they just happened to be that way. We could have picked the other ones and then found out we were wrong, but we didn't. So now just putting it all together, I can go back to my actual image. And again, at the higher camera lengths, I've got to go 90 degrees counterclockwise. And again, make a digital adjustment here just to make the patterns look better. Copy that line over from the image. And there we go. So again, our initial guess happened to be correct. And then same thing here for the shorter camera lengths. Except I know for the shorter lengths, I have to go 30 counterclockwise. Again, I can make a digital adjustment here. Go ahead and copy over that line from the image. And there we go. And so that is a tutorial about how to perform rotation calibration on your TEM. And again, if you have a brand new modern TEM, then this is completely irrelevant because they've all been designed in such a way that you don't have to perform any such calibration. But if you have an older microscope, then this is something that you would possibly need to know how to do. As always, thank you for watching. Please be sure to like and subscribe, share this with somebody that may find it useful. And I always like hearing suggestions from viewers for possible topics for future videos, which is actually where I got the idea to do this video. Thank you again for watching, and I look forward to seeing you again soon.